Hello, welcome back. This is our new topic, topic 4, the periodic table of elements. This is section 4.1, the history and development of the periodic table. Our aim for today is to describe what characteristics were used to arrange the elements in the periodic table. So the periodic table is arranged in a way that tells you a lot about each element. Mendeleev, the Russian chemist, first arranged the elements in a usable way. He tried to arrange them by increasing atomic mass. He found that they had similar chemical and physical properties in periodic intervals. But some of the elements were out of place. So if you switched them around, the properties would be better, but it wouldn't be in order of atomic mass. Then Henry Moseley came along. He was an English scientist, and he used X-rays to identify the atomic number of each element. Of course, we know that's the number of protons. He arranged them by increasing atomic number, and he found if you increase them that way, the properties repeated periodically. The periodic law came about from this, which states that the properties of elements are periodic functions of their atomic numbers. So if you arrange the periodic table by increasing atomic number, we find that the properties repeat. Properties of the elements depend on their location, which is their group number. And elements in the same group have similar properties. So our columns and rows in the periodic table have special significance. The periods are horizontal rows, and groups and families are the vertical columns. The number at the beginning of a period indicates the principal energy level with the valence electrons for those atoms. So the period tells us how many shells, how many energy levels that element contains. So the valence electrons are in that last period, the last number, which is the period. So potassium, which is K, and bromine, which is Br, are in period 4. So they have 4 electron shells, and the valence electrons are in the 4th shell. The number of valence electrons increase across a period from left to right, and this causes different properties for each atom. So as you go across a period, you increase the number of valence electrons. Okay, but every one in period 4 has 4 principal energy levels, and your valence electrons are in that 4th shell. Everything in period 5 has 5 shells, and the valence electrons are in the 5th shell. Our groups are vertical columns. They're also referred to as families. Each element in a group has the same number of valence electrons, which is the last number in your electron configuration. This gives the elements similar chemical properties. So, for example, carbon's electron configuration is 2-4, and 4 are your valence electrons. The group number is the number of valence electrons. For example, group 1 has 1 valence electron. Group 2 has 2 valence electrons. 13 actually has 3 valence electrons. Group 14 has 4 valence electrons. Group 15 has 5 valence electrons. 16 has 6 valence electrons. 17 has 7. And group 18 has 8. So there's definitely you can see the connection between the group number and the number of valence electrons. Okay, so our groups, 1, 2, 3, and then we skip to 13, 14, 15, 16, 17, and 18. Our group numbers correlate to the number of valence electrons. Okay, the transition metals work a little bit differently. They all do have the same number of valence electrons in each group, but it doesn't match up quite with the group number. So types of elements. The first type we're going to talk about are metals. Metals make up 75% of all of the elements. When we colored those yellow today, you could see it's most of the chart. The most active metals are in groups 1 and 2. Metallic properties increase from the top to the bottom in a group. Okay, so as we come down a group, our metallic properties increase. Solids at room temperature. So metals are almost all solids except for mercury, which is a liquid. Most have densities greater than water. So most of them sink in water, except for group 1 elements. They float. They are malleable, which means that they can be hammered into a shape. So if you've ever had any kind of gold jewelry, it's malleable, which means it bends. They're ductile, which means they can be drawn or pulled into a wire. And they have luster, which from earth science, you should remember it means it shines like a metal. Okay, it has a shine to it. They're good conductors of heat and electricity because they have mobile valence electrons. Mobile valence electrons we'll talk about more. It means that they move around. Okay, they're moving. They have a low ionization energy and electronegativity, and we'll be talking more about those in our next section. They lose electrons and form positive ions with smaller radii. So what does that mean? They lose electrons to form positive ions with smaller radii, which means that it's easier to lose than to gain to get a full valence shell. Well, keep in mind a full valence shell would be 8 in the case of where we are. It would want to have a full valence shell. So lithium, as an example, has an atomic number of 3, an atomic mass of 7, and its electron configuration is 2-1. So how many valence electrons does it have? It has 1 valence electron. So if we were to draw the Bohr model for lithium, we would have 2 in the first shell and 1 in the second shell. Okay, this valence electron is easier for it to get lost than it is for it to gain others. It would have to gain 7 more to fill this valence shell. So it wants to lose this, and it will give it to somebody else, to another element, and then it would become positive. Okay, so lithium would become positive when it loses this, and when you lose a negative, you become more positive. So when it does that, it actually gets smaller. Okay, you can see its radius would get smaller if it loses that shell. Okay, so it becomes smaller as it loses that electron. So if you lose electrons, you become positive. So let's look at an example. If we have sodium and it has a plus, that means it's +1. How many protons does sodium have? Here's our periodic table box for sodium. So our atomic number is 11. That's the total number of protons. The number of neutrons, remember, neutrons plus protons gives us our mass number. So if it's 23 for mass, it would have to have 12 neutrons. And in the neutral atom, we would also have 11 electrons. However, we have a +1. So remember that your protons minus electrons equals your charge. So if we have 11 protons and we have a charge of +1, we must have 10 electrons, which means if you've gone from 11 electrons to 10, it has lost an electron. Transition elements are in groups 3 through 12. This is the middle of the periodic table, plus those extra rows that they put onto the bottom. The outermost orbitals are being filled. They are hard solids with high melting points, so they melt at high temperatures. They have multiple positive oxidation states, so they have many different charges that they can have. Several of them do. They also have a color. Okay, so the center section here is the transition element section. Metalloids are right next to the staircase line. That's the staircase line that we colored them light green today. So boron, silicon, germanium, etc., those are our metalloids. These are semi-metals. So they are between metal and nonmetals. They have similar characteristics to both. They are an intermediate type of element, which means they're in the middle. They have both metallic and non-metallic properties. So this is the line that we colored today. Nonmetals. These include solids, one liquid, which is bromine, and gases. Gases or molecular or network solids at room temperature. They are brittle, which means they break easily. They have a dull surface, so they're not shiny. They have a high ionization energy and high electronegative values, which again, we'll talk about that later on. They're poor conductors of heat and electricity. And they gain electrons to become negative ions with radii larger than their atoms. So what does this mean? That they're gaining electrons to become negative with radii larger? Well, it's easier for them to gain electrons than to lose. Okay, oxygen has an atomic number of 8 and an atomic mass of 16. Its electron configuration is 2-6. Remember, 8 can fit into this last shell, and it only has 6. It is easier if we draw oxygen in a Bohr model. Okay, this is our nucleus. Our first shell, we have 2 electrons. And our second shell, we've got 6. It is easier for oxygen to gain 2 more electrons to fill its shells. If it fills in its shells, it will have a larger radius, which means it has gained 2. If you get more electrons, you get negative. Okay, so it would have a larger atomic radii. So nonmetals, again, gain electrons and become negative. If you get more negatives, you become more negative. So if we have oxygen with -2 charge, the number of protons in oxygen will always be 8. The number of neutrons, remember we take our atomic mass minus our atomic number, so there are 8 neutrons. Now electrons would also be 8 in the neutral atom. However, we have a -2 charge. Since protons minus electrons equals our charge, we've got 8 protons and our charge is -2. So we must have more electrons than protons to be negative. So 8 minus 10, it gives us our -2 charge. Our noble gases are our group 18 elements. These are unreactive. They don't have the properties of nonmetals. They also don't react with anything. They have a full valence shell. All 8 are full in their valence shell. Helium only has 2, since it only has 1 shell, so both are full. The full 2 electrons fill its shell. So they don't get to react with anything. They have nothing to give or to take away, since they're already happy. They're stable with their full valence electron shell. Allotropes are nonmetals that can be in 2 different forms in the same phase. So for example, oxygen, O2, and ozone, O3, are both gases. Carbon can be both graphite and diamond, okay, depending on how it formed. They have different physical and chemical properties, even though they're made of the same element, but based on how they were formed, they have a different structure. Okay, here's our noble gases all the way here in group 18. And another look at our periodic table of elements showing the gases, okay, as we colored them with a red dot today. So some practice questions. Atoms of metals tend to. So what do metals do? Do they gain electrons or lose electrons? Okay, metals tend to lose electrons. And when you lose electrons, you get more positive. If you lose a negative, you become more positive. So number 2 here, lose electrons and form positive ions. Which salt has an ion that forms a colored solution? The key here is that it's colored. Okay, our transition metals have colors. So we're looking for the transition metal here. Okay, and the transition metal here is nickel, which is choice 3. A magnesium atom differs from a magnesium 2+ ion in that the atom has a. So if you have magnesium, magnesium has 2 valence electrons. If it loses those 2 electrons, it becomes positive. Okay, it's losing a shell, essentially. If it loses a shell, it's going to have a smaller radius. So the magnesium atom has a larger radius. When you lose 2 electrons, you become smaller. The presence of which ion produces a colored solution? Again, our transition metals have colors. So this would be a transition, which is our iron ion. And that completes this section of notes. See you next time.